we're not meeting in person, I'm gonna post that as a PDF after this, and then I'll have a few physical copies before in case somebody, forgets. But long answer, yes.
Okay, thank you. I have a question.
Hmm.
Were you gonna kind of overview a bit of what you went over last week?
Yeah, so I
Or
was
you
gonna
just starting
start
from
back
here?
up here at acid base, um, and then go do the review that I posted. So the review is pretty lengthy. I made sure to basically give you an example of every single question that's on there. Um, so that will also in turn give us some review of the pH stuff.
Okay, and will you be available to meet with? Because I wasn't there last week. I went over your what you sent, but it still needs you to put your stamp on it for me to make it all make sense for me.
Yeah, absolutely. I'll be there at 5
Okay.
p.m. before the midterm.
Okay, thank you.
All right. Any last question? Okay. So this is where we left off. Um, I wonder what happens if I put it in presentation mode. Okay, this is where we left off. So I I think this is where we left off. To be honest, I didn't check my notes, but I think this is a good starting point as a refresher. So we had introduced the idea of pH and the concentration of acid and base, and how every solution has a little bit of acid and has a little bit of base in it. It's just which is in higher concentration is what we determine if the solution is acidic or basic. And so then I gave you this acid-base square where the four things that we have pH, H plus concentration or acid concentration, OH concentration or base concentration, and then POH are all related to each other in this square. And you get this on your reference sheet. And basically, pH is a log measurement of the amount of acid, and POH is the same, but for base. And together they should add up to the number 14. Um, so we had our KW formula that we learned about, where 1.0 times 10 to the negative 14th always equals the product of OH times H plus. That's supposed to be an equal sign, sorry. All right, so that's that there. I think we also introduced this where pH is the negative log of H plus. But what I don't think we had quite introduced yet is the inverse of that formula. So say you were given pH and you're trying to find the H plus, which we're going to do some examples of in the next slide, or if not on the review, is the inverse formula. And so this formula right here mathematically is the opposite. Now, I could show you mathematically, but we'll just take my word for it that if you take 10 to the negative pH, that should give you the H plus concentration. So let's dive into this a little with some practice problems. So pH is the inverse of pH. They have to equal 14. All right, so here's some practice, specifically with POH. So this says, what is the pH of a solution that has OH? And it gives us this value. So we're trying to find pH and we have OH. So I'm going to go back a few slides back to our acid base square. So we have this and we want to get here. All right. So it looks like we should use this formula. POH equals the negative log of OH. All right. So I would say POH equals negative log of 5.4 times 10 to the negative fifth. All right, let me plug that into my calculator. I'm sure I have it pre-solved somewhere, but I just don't have those notes in front of me. All right.
Are you still gonna show us how to plug that into our calculator?
I mean, I can if you come to office hours before,
Okay.
but unfortunately, like, it would be really hard to do it over Zoom. Sorry, I'm using my iPhone calculator. I'm just throwing myself for a loop. Okay. So I got POH equals 4.27. All right. And like I talked about, using this formula with pH, a good way to check yourself is that you're somewhere near your exponent number. All right. Doesn't matter if it was 5 point something or maybe even 6. But if I'm in the 11s and my exponent was a 5, that's a red flag. Additionally, you want to make sure that your pH or your pH is somewhere between 0 and 14. It has to be on that scale or else it's not correct. All right. So here I found the pH, or I'm sorry, I found the POH given pH. Next, we want to find the POH again, but this time, and this is where we have to be careful, we are given the concentration of acid. All right. So let me just erase this, and then we'll go back a couple slides. And then since this is being recorded, you can come back and get that answer later if you need to. All right. So this time we were given this, but we want to get here. And so there's no direct relationship, right? I either have to go this way or this way. I usually prefer to go this way, whatever way includes this pH plus POH equals 14, because it's just mathematically a little bit easier to do, a little bit simpler, less room for error. If I went this way, I have to use the KW formula, and that one's kind of a little, there's more room for error. So I'm going to go this way. So there's going to be 2 steps here. My first step is I'm going to find pH by using the negative log formula. So I'm going to use that same formula that I just did in the last problem, but this time it's going to give me pH. And then second, I'm going to use the relationship between POH and pH, knowing that they both have to equal 14. All right, so now we got a mess here. Okay, so I'm going to find the pH equals negative log of the H plus concentration, which in our case is this. So the negative log of 7.3 times 10 to the negative 10th. All right, and I would plug this in my calculator. So a good way to, since, unfortunately we lost 2 days here due to the weather, is maybe if you go, when you're going back and doing the review, which I encourage you to do after this session, make sure you're getting the same numbers in your calculator as I'm getting, so that way you're using your calculator correctly. I could even round this to 9.4. All right, so that's my pH. All right, 9.14. It's close, right? It's close to a 10. So I know I'm on the right track. So I just went from here to here. Now I want to go to POH, and now it's kind of a mess, but I want to use this relationship here where POH plus pH equals 14. So since I know that, let's do a different color for the second step. So I know that POH plus pH equals 14. I know that my pH is 9.4. So if I subtract 9.14 from 14, I should get my POH. At 4.86. All right, and that would be my final answer, 4.86. Any questions? All right. So this time I actually included the square on my slide. Thank you, previous Kayla. All right, so here's an example OWL question where it basically tests you on this scale, but it asks you to rank the solutions on their acidity. All right, so acidity means like the most acidic would be closest to zero. The pH would be. All right, so these drop down menus, it says like most acidic, least acidic, and then I think it says like intermediate or something like that. So if we're going to be ranking something on its acidity, I think it makes sense to make sure that they're all in pH. And so solution 1 is already given to us in pH. Great. Solution 2 is given to us in H3O plus, which is the same as H plus. So they've given us this. And we want to go to pH. We want to compare everything in pH. So we're going to do the negative log formula. So I do the negative log of this formula, 10 to the negative 8, which actually, I know this one off the top of my head, would be pH equals 8. Right? And then lastly, we have a concentration solution 3 is given to us in OH. So this is another two-stepper because there's not a direct relationship here. There's not a direct relationship here. And so I either have to go this way or this way. And like I just said with the previous problem, I always like to go in the direction that includes the pH plus POH formula, this formula, just because it's less room for error. So first, I would find the POH, right? This is my first step, finding the POH using the negative log. So I'd say negative log of 10 to the negative 12, which happens to be 12. And then pH plus POH is my second step. So this is step 1. And then here's step 2. So that always has to equal 14. And so if my POH is 12, then my pH has to be 2. All right, so now I have them all in pH, so I can rank them. We'll go back to red for this. All right, so the most acidic is whatever's closest to 0. You have an echo. Yeah, I'm sorry. Usually people can't hear it, but unfortunately, is it really, really bad? Because it's my iPad and I can't get it to go down to a volume. Oh, this is a direct message. Okay, we'll ignore that. Okay, so most acidic, closest to 0. So the most acidic is pH of 2, right? That's of our 3 solutions, that's the closest to 0. All right. Least acidic is going to be closest to 14. So that 12. And then I can't remember what the actual drop down says, but like intermediate, maybe. All right. So that is determining acidity or pH. All right. This isn't anything we need to memorize. I think I just like this chart because whatever's a strong acid, so like that's not the one I want. Here, hydrochloric, that might be kind of familiar for us. HCl, that's a strong acid. Strong acids make really weak bases. All right, so whatever is high up here, strong acid is a weak base, and the same thing vice versa. So this like hydroxide that we've been talking about down here, OH, that's a really strong base, but a weak acid. Right? So again, you don't need to memorize this table or anything. I like to show it as a visual. All right. And so the last thing we want to talk about real quick are buffers. So buffers are weak acid solutions that resist major changes in pH. All right. So um, they're in the solution and they're there to basically help protect it. So here's an example of where we have water and just water. And when we add a HCl, a strong acid to it, it goes from a pH of 7 to a pH of 3. It basically becomes acidic. But if we were to take that water and put in buffer, whatever that buffer system is, now when we add HCl, it will become a little acidic, but it's going to resist major change. It won't go from 7 to 3. It goes from 7 to 6.9. And the same is for if we were to add base, a strong base. So without a buffer and we add base, it goes from pH 7 to pH 11, basically becomes basic. But when we have buffer, it goes from 7 to 7.1. So a buffer resists major changes. All right. And so one of the areas we have these buffers are in our blood. So we have this buffering system in our blood, sodium bicarbonate. No, not sodium bicarbonate. Sorry. This is something bicarbonate. What is it? I can't think of the name, and I don't know why I can't think of the name. Um, but we have this in our blood, right? And it goes back and forth between these two forms, where it basically is taking on a hydrogen versus releasing hydrogen. And so that's why when acidic solutions come into the blood or super basic solutions, we can resist change. We our blood stays between 7.35 and 7.45, which is normal and happy, right? It doesn't become 6 or 9. When we drink coffee, we know that coffee is a little acidic, right? Our blood doesn't become acidic. It buffers and stays within normal range. All right, and then this is just kind of a random slide here, but we just need to talk about it real quick. So on the exam, you have to define um, reduction, I think it is. They always kind of switch it between oxidation and reduction because these two terms are like opposites of each other. So we'll just define what they are. So oxidation is when you are losing an electron. Right? Usually to solution. That's, it might not make any sense, but just go with it. All right, reduction is gaining an electron to the solution. So what you need to know is reduction is gaining and oxidation is losing. And there happens to be a handy mnemonic. So oil rig, oxidation is losing, reduction is gaining. All right, so if you can remember oil rig, then you'll be set for this question. All right, so that's the end of our lecture 3. Any questions before I then pull up the review? Okay, we're gonna jump right into the review. So I gotta escape out of this. Okay. So this review, I posted it earlier. I had to make an edit to it because the file I uploaded wasn't the right file at first. But anyways, so it's got 45 questions. We're gonna power through all of them, hopefully. And so this is exhaustive, though, of the things that you'll see on your exam. Your exam is 50 questions, though. So there's two questions, I think, right here. So you have this concept is on there twice. That's what that times two means. And then it was the naming. Yeah. And then this concept is on there basically 4 times. So that covers your other 5 questions. All right. But we'll start at the top. So I believe so the order of this is just a random order because I just went in there and generated you know, to show me the student version of the test, and you guys get them all in random jumbled order. So this is just in jumbled order. There's nothing significant about that, but I'm gonna try to help guide us to what lecture it was in as we go through this. So the first question is about pH.
Professor Daniels,
Yeah. What's up?
will we still get a copy of this review?
Yeah, so it's posted online and then out today.
Okay, okay, thank you.
All right. Any other questions?
And then this review is the same as the other review, just mixed.
Can you say that again? Like, what do you mean
Is
other?
this
The one that's already posted by like Arizona College?
I think so. It started with like mass, matter, weight.
Yeah, so mine is a little bit more pared down, if that makes
Oh,
sense.
gotcha.
Mine, I literally went in there and looked at the test and said, okay, I'm gonna write a question that looks exact, like I said,
Okay.
this writing looks exactly like the test, only I changed to a different number. All right. The one that's already like posted when the Canvas shell gets posted, that's like
Mhm.
Arizona already has that embedded every time they post the Canvas shell. And that is more like I don't know how to say it. Like there's stuff on there that's not necessarily on the exam.
Oh, okay.
So
Okay, gotcha.
it's still a good resource if you want extra practice.
Okay.
So what we're looking at now, this is from you.
This is from me, correct?
Okay.
All right. So our first question, so like I said, I just took the questions, put in different numbers if they were like mathematical ones. You'll see later, like there's some definition ones. I just told us to like define it. All right. So question 1, what is the hydroxide ion concentration of a solution whose H3O plus is 1.0 times 10 to the negative 10? So this is a pH question. This came from our lecture 3, the one we literally just finished. All right. So if I see a question on there with H3O plus, H plus, I'm going to want to be heading to that acid base square, which is going to be on your reference sheet. All right. So when we head to the acid base square, which I'll come back to here. No, let's go to this one. All right. So the question, and I know I just moved away from it, I'm sorry, but it said, what is the hydroxide ion? So it wanted to know what's this, and it gives us this. All right. So the only way to get there is to use this KW formula. So this formula, it's on there, I'm just rewriting it, is 1.0 times 14 equals the H plus times the OH concentration. So when I go back, right? So I need to use, so the hydroxide, that means OH. So I need to use this KW formula where 1.0 times 10 to the negative 14th equals H times OH. And so since I'm given H3O plus, which means the same as H plus, I'm going to plug that in here and then solve for OH. So I'm going to manipulate the formula first. Divided by h plus. All right. So when you do this, you want to make sure you use parentheses when you plug into your calculator, or else the order of operations is not going to work. So I would type into my calculator parentheses 1.0 times 10 to the negative 14th. However, I do that on whether it's a calculator or sorry, a caret tool, or if it's like a different tool. So this is negative 14th divided by open parentheses 1.0 times 10 to the negative 10th, close parenthesis. All right. So when I plug that into my calculator, I'm gonna put the answer in blue because that's kind of getting messy over here. I got that the OH concentration equals 1.0 times 10 to the negative, oops, not fifth, fourth molar. Any questions? All right. Second question. I see OH again. So that's cueing me. I see this OH. That's cueing me that this is again a pH question from lecture 3 and that I should head to the acid base square. All right. So this time it's giving us the pH and it wants us to find OH. So again, we're trying to find OH, but now we're coming at it from a different angle. All right. So I am going to, am I going to erase or am I going to move on? We'll move, I guess. Oh yeah, I have room. Okay. So now we're given this guy and we're trying to find OH. All right. There's no direct relationship. Can't do that. So we have to do 2 steps. All right. We could go either way, but like I said, I always like to prefer this side where we use that guy just because it's less room for error. So this is going to be our step 1, going from pH to POH. And then our step 2 will be going from POH to OH. And in this case, we're going to use the 10 to the negative POH formula, which is one that I haven't given us an example of yet. No, actually, I'm going to delete this. It's getting really messy. Okay. So, step 1, we want to go from pH to POH. All right. So that formula is pH plus POH equals 14. We have our pH, so I'm going to go ahead and plug that in. So 14 minus our pH. So I plugged it in and manipulated the formula at the same time. So 14 minus 3.34 would give us our POH. And that is 14 minus 10.66. All right, so that's our step 1. We found the POH. Step 2, we can now go from POH to OH minus. All right, I'm going to do this in blue so it's less messy. All right, so that formula is that OH equals 10 to the negative POH. All right, so I'm going to take my answer from step 1 and plug it in here. All right, now your final answer is not this. You have to plug it into your calculator. You can't have a decimal in your exponent. You have to plug this into your calculator. Okay, so let me do that real quick. 10.66 to the, no, clear. 10 to the 10.66 negative. All right, so then I got 2.818, and I could even round that to 19 actually, times 10 to the negative 11. So now we're doing that one negative log formula in reverse. So the rules about looking at the exponent still apply. So here, my exponent was around 10.66. So it makes sense that my exponent would be to the nearest whole number, right? 11. We just need to figure out what this up front part is, and that's what the calculator is going to do for us. All right. So the final answer would be 2.19 times 10 to the negative 11. Any questions?
Yes. How did you make it to be 2.19 if it was 2.818?
Did you get 2.818?
If
Yeah,
that's
so
what
I got 2.1877. So I
okay.
rounded based off that. Um, if you're getting something slightly different, but like you still got 2.1 something, luckily the test is multiple choice. So you like it'll be obvious which answer it is. It doesn't come down to rounding that like to that precision.
That was just my fault. I heard it wrong.
Oh, okay. I might have
Okay.
also said it wrong.
Okay.
All right. So we'll look down here at question 3. I'm gonna go ahead and erase this. All right, question 3. And again, this might be sound like it's crazy writing, but I just wrote the question as if it says on the test and then just inserted a different number for practice. So I see pH again, so I know that this is a pH question and I should be heading to my acid-base square. But first, let's try to figure out what the heck I'm doing here. So I'm given H3O plus concentration. A client with respiratory alkalosis has an H3O plus concentration of yada, yada, yada in the blood plasmin. What is the pH? All right. So I'm going to head to my acid-base square. So we're given this and we want to get here. So that is the negative log formula. All right. So just to reiterate that formula, it's pH equals the negative log of H plus, which is the same as H3O plus. So negative log of 5.76 times 10 to the minus 4. So then I would plug this into my calculator, and I'm looking for a pH value that is 1 between 0 and 14, because that's what the pH scale is. Next, I know it's going to be near 4. So when I plug this into my calculator, I got 3.24, which fits that criteria. Any questions? All right. Question 4. So this still has to do with pH stuff, but it's not a math one. So we don't need to head to the pH square. This is more understanding fundamentally what what pH is. So which term best describes a solution with a pH of 3? So let's remind ourselves what the pH scale is. So it's 0 to 14, right? The pH scale. With 0 to 7 being acidic, 7 to 14 being basic, and then 7 itself being neutral. I should have said 0 to 6.99, but I think we get the point. So if it has a pH of 3, it falls between this 0 to 7, meaning it's going to be acidic. All right. If it said pH of 12, then it would be basic. All right. So 7 is the cutoff. Below it is acidic, above it is basic. questions?
Yes, I have a question. So how do we know when it's neutral?
Neutral is 7.
Okay, when it's 7. Okay.
Yeah, when it's exactly 7.
Okay.
All right.
Thank you.
Yeah. So 5 and 6 are still pH questions, but again, they're more like the I don't know. I want to say fundamental, but that's not the right word. But they're not the math ones, all right? So 5 ask what is the formula of the conjugate acid or conjugate base of HCl? So a base is when um it wants it doesn't have a hydrogen basically. All right. So right now HCl is an acid, it has that hydrogen. So the conjugate base would be when it loses it. So it'd be Cl. And the um because that H is a positively charged, HCl is neutral, meaning I take away a hydrogen from it, it's going to then become negative. So Cl minus would be the conjugate base. You only have one of these questions, but I decided to put another example here for practice. So this should really look like this. H3O with or HCO3 with the 3 being tiny and then the minus sign being up here. I just got lazy and didn't format it. All right, so say we were to ask for the conjugate base of this guy. So we're gonna lose a hydrogen, so it'd become CO3, and then that minus then becomes 2 minus. So this is the conjugate base. This guy, I purposely chose it as an example because it has 3 different forms, basically. It can also have a conjugate acid where it takes on another hydrogen. So it becomes H2CO3 neutral because we'd be adding a positive to this negative. You only need to know how to do conjugate bases for the exam. So drop a hydrogen, basically. Number 6, we're still in our pH stuff. This is kind of where we started with our pH, which was determining which is a base and which is an acid. So this one only has a forward arrow, meaning we're only classifying what's on the left side or the reactant side. All right, so we just need to track the movement of the hydrogen so we can determine which is the acid and which is the base. So the first step I like to do is just pair them up. What looks like pairs? So H2SO4 looks a lot like HSO4 minus. They're a pair. H2O looks a lot like H3O plus. It's just the movement of a hydrogen, so they're a pair. So it looks like H2SO4 loses a hydrogen. It's got one less hydrogen over here. So he threw the ball being a hydrogen atom. So he's an acid. And then H2, it looks like he caught the ball, again, ball being acid. And so, I'm sorry, H. And so he's a base. So when it loses a hydrogen, it's an acid. When it gains a hydrogen as it goes to the other side, it's a base. All right. So this would be an A, B, C, D question for you. And so if it said H2SO4, H2O, H3O plus, NHSO4 minus. So you're looking for the base on the reactant side. So you can automatically rule out these two things because they're on the product side. And we just determined that the water is the base, H2O. Any questions? All right. So now we're out of pH stuff. I might have thrown another pH at the end if I can remember. Yeah, there's another pH in there, but we'll get there. This was still lecture 3 though. This is when we were talking about solutions. All right. So we talked about concentration of solutions. There was 2 different types of ways we can take the concentration. There was percent weight volume. There was also percent volume volume and percent weight weight, but they all kind of work the same. So we really just focused in on weight volume. There's also molarity or big M, which we talked about quite a bit. So these are all examples of solution stuff. Number 7 is where we're going to calculate the concentration of weight volume. Number 8, we're going to calculate the concentration of molarity. Oh, number 9 is not the question I thought it was. Never mind. Okay, so the formula, looking at number 7, the formula for weight volume is basically you want small over large times 100. And specifically, you want to be grams over mils, but usually the small over large covers that. So we're given grams, 2.13 grams, but instead of mils, we're given liters. So we need to change this to milliliters, ml. All right, so we talked about this. King Henry died by, come on, drinking chocolate milk. All right, so I recognize we didn't spend a whole lot of time on this and that we've been kind of glossing over. And that, I wish we could spend more time on. I apologize. Just the way the course is designed, there's like 2 questions on the test where you need to know how to do this. And so that's why I didn't focus in a lot on it. But so the acronym is King Henry died by drinking chocolate milk. The only time you ever really use it is to go between mils and your base unit. So the M for milk is mils, and then B is your base unit. So in this case, liters. This is our B. All right, so it's your base unit is whatever that word is without a prefix. So if it's liters, meters, grams, all of that. So we want to get here, and right now we're here. So if we bunny hop 1, 2, 3, we had to bunny hop 3 places, which means I'm going to move the decimal to the right 3 places since I bunny hopped to the right. So 0.34, 1, 2, 3 translates to 340 because I'm adding a 0 here, mils, right? And before that, you might have been saying, Kayla, small divided by large, 0.34 is not larger than 2.13. But when we change it to mils, yes, it is. All right. So we're doing 2.13 grams over 340 mils, and then that times 100 to make it a percent. Again, I'm running out of room, but let's look. 2.13 divided by 340 times 100 happens to be less than a percent just because the numbers I made up are weird. But we have final answer 0.6 We're going to round to 3. So 0.63%. Now, this question is worded exactly like your question on the test. So it tells you to do grams divided by mils. You just have to remember the times 100 part. And if not, I believe I have the formula on the formula sheet. All right, next. Well, first, any questions? All right, so that was one way we can measure concentration. The other way, which we spent a little bit more time on, was big M. All right, and so that's our next problem here, number 8. So a normal saline solution used for IV drips contains 1.12 grams of sodium NaCl, or sodium chloride NaCl per 0.7 liters of solution. What is the molarity? So molarity, big M, and this formula would be on your formula sheet, but big M equals moles over liters. So this time we have grams and we have liters. So this time we have the liters part. We don't have to change there, but we will have to go from grams to moles. All right. So hopefully, and I'm crossing my fingers here, when I say you have to go from grams to moles, you aren't freaking out because that's a foundational step in a lot of these problems. But if you forget, you go from grams to moles using the molar mass, all right, MM, and that's unique for each compound, all right? So you would find them by adding together the decimal numbers on the periodic table. But I might have already mentioned this. If I haven't, here's my disclaimer. So there's a lot of problems on the exam where you're going to need to know molar mass, okay? And then there's one question that tests you on your ability to calculate it. So what I do is on the reference sheet, I give you a bunch of molar masses for all the problems. And I give you almost like more than you would need. So that way I'm not like, we're not cheating here, I guess, basically. I give you more than you need. You just have to be able to identify the compound. And then I don't give you the one in which they're testing you for how to add. So, for example, if they say, if the question that tests you on your ability to calculate molar mass is water, then I won't put that in the bank of molar masses, but I'll make sure that every other molar mass that you would need for the test is on there, and then I might throw in a few more just to, you know. So you do not need to calculate NaCl. You would just go to the reference sheet and it would tell you that NaCl is 58.44 grams per mole. So you need to know how to set this up. 1.12 grams, that's going to go on top. We want grams to cancel, so we're going to put grams on bottom. His partner is moles. Moles is going to go on top. This number is always married to the gram, so since I put grams on bottom in order to cancel, I need to put this number with it, leaving 1 mole on top. Then I would plug and chug into the calculator, 1.12 divided by 58.44. And I get 0.019 moles of NaCl. So this is great. We are already in the problem given our liters, and now we have our moles. So now I can finally plug in this formula. But I've used a lot of space here. It's getting kind of messy. So I'm going to change to blue. All right, so molarity equals moles over liters. Moles we just solved for here is 0.019. Liters we got from the problem, 0.7. And so when I do 0.0 0.19 divided by 0.7. I got point, again, running out of room, 0.027 big M, which would be our final answer. Any questions? All right. Gonna erase and go to question 9. So question 9, I honestly can't remember if we talked about this in lecture 2 or lecture 3, to be honest. I don't know. But it's the gas. All right. And we know it's one of the gas law ones because it's got the word gas in it, right? That makes it easy. And so there's 2 gas laws that you need to know. Again, you'd be given this on a reference sheet. One of them is the partial pressure, and the second one is the ideal gas law. All right. So partial pressure is just the one where the total pressure equals the individual pressures added up. All right. So how can I identify in the, oh, sorry, and the ideal gas law is the one where you say you have all those 5 different variables, PV equals nRT. So if you see a question that has the word gas in it, you first need to identify which gas law problem it is. Which formula do you need, basically? And so this one tells me I see the words total pressure and I also see the words partial pressure. And so that's going to tell me that it's the partial pressure law. All right. So it's the easy one where you add them all up, basically. So here it says it's total pressure. So P total equals 1.07 atmospheres, which we know must be the sum of all the pressures. And so for this one, it looks like there's just neon and argon, so there's just 2 gases in it. We know that neon is 0.87, or I'm sorry, 0.89 atmospheres. And then we would just we're trying to figure out what the pressure of argon is. So we would just subtract this from both sides. And argon's partial pressure would be 0.81 atmospheres. All right. All right, so number 10 brings us back to lecture 3 when we were talking about solutions. All right. So this question's got a lot of words, but what I want you to look for is this word diluted. So there's a lot of numbers going on. I don't know what to do with them, but I see the word diluted. All right. Well, there was an equation that we learned about in the solutions, which was called the dilution equation. So when I see a problem that has the word diluted in it, I know that this must be the question that's testing me on the dilution equation. And so the dilution equation is C1V1 equals C2V2. It's the one that's basically a proportion. All right. And so how I like to set all of these up is where I come over here to the side and I list all my variables and figure out which is which. All right. So the beautiful thing about the C1V1 equals C2V2 is units don't matter as long as they're in the same unit on both sides. So C being concentration, as long as it's molarity on both sides, doesn't matter. So as I read the problem, a student dilutes 34.5 of a 2.75 molar nitric acid solution. So those first 2 numbers, they sound like my initial because they come first in the problem and they're married together with the word of. So that indicates to me that those 2 are my initial. So my initial concentration, 2.75 molar. and my initial volume 34.5 milliliters. All right. It says they dilute it to a total volume of 300 milliliters. So this is going to be my volume 2. And then they want to know what is the new concentration. So this happens to be what I'm solving for. So like I said, this equation, units don't matter as long as they're the same on both sides. So concentration 1 is given to me, concentration 2 I'm solving for. So if concentration 1 is in big M, concentration 2 is going to come out in big N. It's more the volumes we have to worry about. So volume 1 was given to me in mils and volume 2 was given to me in mils. So luckily, no problems there. So now it's just a matter of plugging this into the formula. So I'm going to manipulate the formula first to where I solve for V2. So if I wanted V2 by itself, I'm sorry, C2 by itself, I would divide each side by V2. So I get C2 equals C1 times V1 divided by V2. And then I can plug in my numbers. So I have 2.75 times 34.5 divided by 300. All right, so 2.75 times 34.5 divided by 300 into the calculator equals 0.316 big M. All right. So it's also called the dilution equation. So it makes sense that my concentration 2, my final concentration is diluted from concentration 1. So it's less than concentration 1. So I did the math right if it comes up to a number that's smaller than C1.
Can you explain the part where you, I guess the C2 equals C1 V1 divided by V2? I can't understand how you went from the C1 V1, C2 V2 to that.
All right, so all I did was take this formula and manipulate it to where I put the variable that I'm trying to solve for by itself. All right, so this is algebra, right? So if I want to get the variable that I C2 by itself, then I'm going to divide each side by V2, where I then have it on top and bottom, so it cancels. But what I do to one side, I have to do to the other. So I come over here with V2. All right. So then I just flipped it when I rewrote it. So C2 equals C1, right? Oops. Sorry, on my end, okay, there we go. C1 V1 divided by V2. I just flipped it then. Does that make sense?
Yes, thank you.
Yep, that's fine. Any other questions? All right. So erase this. All right. Number 11. So this also has the word gas in it, right? So it's indicating to me that it's going to be one of our 2 gas law problems. So you already know that it's probably going to be the ideal gas law given the fact that we've already encountered our pressure one, but say you're on the test and you get this in a scrambled order. How do you know that this is the ideal pressure and not the partial pressure one? All right. Basically, because it gives us a bunch of variables. We got moles. Sorry, I was trying to underline. We got moles. We got liters. We got temperature. And we're trying to find pressure. All right. When it's got all these variables, it's indicating me that it's the ideal gas law, which is, and this would be coming from a reference sheet, PV equals nRT, where R equals 0.0821. Again, that would be on your reference sheet. You just have to go pick it out of the formula sheet. So Because there's 5 different variables, I like to set this up the same way we set up the last one, where I list all the variables on the side. All right, now with the ideal gas law, it's very picky about its units. Pressure has to be in ATM or atmospheres, volume has to be in liters, N has to be in moles, R is a constant, we don't have to worry about that, and temperature always has to be in Kelvin. So in your problem on the test, it's going to look exactly like this, but different numbers, where it's going to give you the moles already in the correct unit. It's going to give you the liters in the correct unit. The one unit that you're going to have to watch out for is the temperature. It's going to give it to you in Celsius, and you have to put it in Kelvin for it to work for this formula. So we're going to do temperature in a few practice problems, but just a refresher that Kelvin, K, equals Celsius, C, plus 273. So 25 plus 273 equals 298. All right. So that is going to be the one thing you have to change. So pressure you're solving for. That's your X or your question mark. V from the problem, 6.75 liters. N, getting this from the problem, 3.45 moles. R, that constant, I'd be pulling this off the reference sheet, 0.0821. And then T, 298, because we had to change it to Kelvin. All right. So now it's just a matter of plugging these variables into that formula. We're solving for P, so I'm going to manipulate the formula first. So to get P by itself, I'm going to divide each side by V. So P equals nRT divided by V. All right. And then I can plug in my numbers. 3.45 times 0.0821 times 298 divided by 6.25. All right, so I'd make sure I plug this into my calculator correctly, multiply across the top, divide by the bottom, and you would get a final answer of 12.5 atmospheres. Any questions?
Yes, how did we get the R again?
The R is going to come from the reference sheet. It's always the same. It's a yeah. All right. So number 12. Oh, gotta delete this. Okay. So, ooh, 12. All right, so this has to do with gases again, although it does not include the word gas in it. I'm sorry, this has to do with pressure. All right, so there's a bunch of different units for pressure. If you remember, I showed you this whole line where it was like 1 atmosphere equals this equals this. And so this would be on your reference sheet. Let me see if I can go find it in the lecture. I can't, here it is. All right, so 1 atmosphere equals 760 millimeters mercury to a 760 torr, blah, blah, blah. So this line will be on your reference sheet. You just need to know how to use it. All right. So real quick, if I go back here, it says that we're trying to find ATM, atmospheres, and we're given millimeters mercury. So I need to know the relationship between millimeters mercury and ATM. All right. So I would go to my reference sheet. I would go look at this formula. And it looks like 1 atmosphere equals 760 ATM. So 1 atmosphere equals 760. Oh, sorry, millimeters mercury. I was saying ATM and saying atmosphere. Okay. So then I'm going to set this up like any of my other conversions where I start with my given 345 millimeters mercury. I put that on top. I put what I'm trying to get out of on the bottom so they cancel. So I'm going to put millimeters mercury on the bottom and what my desired unit is on top, atmospheres. So now the millimeters cancel and my desired unit is on top. So 1 atmosphere equals 760 millimeters mercury. So then it's just a matter of plugging this into my calculator, doing 345 divided by 760, and my final answer is 0.45 atmospheres. All right. So next, we get into some problems that have to do with stoichiometry. All right, so that was at the beginning of lecture 3, stoichiometry. And so I know it's a stoichiometry problem if they give me a balanced equation. That is already clue 1. All right. And if you remember, stoichiometry is when we used that stoichiometry map. So let me go back here. All right, so this map would be given to us on the reference sheet. Okay. So, given the following equation, determine how many grams of iron, so how many grams of iron are produced from 4 moles of chlorine. All right, so if I didn't already know that it was a stoichiometry from the fact that they gave me a balanced equation, I should be cued in to the fact that it's stoichiometry based on the fact that it's 2 different compounds. I'm trying to switch compounds on top of switching units. All right. So when I do that, I have to refer to that map. All right. So we're starting in moles of this guy, and we're trying to get to grams of this guy. All right. We can only switch substances when we're in moles. All right. So right here, we can only switch substances when we're in moles. So luckily, we already start here in moles, and we can immediately start by switching substances. All right. And then we're going to need the molar mass to then go to grams of our final product. But since we're starting in moles, we're basically starting here. All right, so I'm going to start with my given on top, 4 moles of Cl2. That's an ugly 2. So I start with my given on top, and I can switch substances. So I can put moles of Cl2 on bottom, and then I want to go to moles of my desired substance on top. So in this case, iron. All right. So then now I need to figure out what their relationship is, and that's going to come from the coefficients of the balanced equation. So 2 moles for every 3 moles of chlorine. Chloride. All right, so now I'm out of moles of chlorine and into moles of iron. So I'm halfway there. So now if we go back to our stoichiometry map, I'm here. Now I need to go to grams. And so I'm going to need the molar mass of iron. All right. So again, like I said, you can go to your reference sheet to find all the molar masses. So in this case, I'll give it to us. It's 55.85 grams per mole. All right. So I want moles of iron on bottom because I want them to cancel, and then I want grams of iron on top because that's my desired unit. This number always travels with the gram, so since I determined to put the gram on top, I'm going to put that number on top too. And then that leaves me with 1 for the bottom. So now I'm out of moles of iron and into grams of iron, which is great. That was what I was trying to get to in the end here. So now I can multiply across. So 4 times 2 times 55.85 divided by 3 into my calculator. And you get 148.99 grams of iron. Questions?
And so we multiply straight across the top and then divide
Yes.
on the bottom. Okay.
All right. 14 is also stoichiometry. I know my first clue is that I'm given a balanced equation. All right. But then I'll get my second clue once I read the problem. So, given the following equation, determine how many moles of iron chloride are produced from 0.35 moles of chloride. So I'm switching substances. That is stoichiometry. So I'm given moles and I want to get to moles, but of a different substance. So if I go look at my map, that's just a one-stepper. Going from moles to moles is just a one-stepper. It's just using those coefficients from the equation. So we're basically just going to do the first step of what we just did in the last problem. So we're going to start with our given 0.35 moles of Cl2. We'll put moles of Cl2 on bottom because we want them to cancel. We can only ever go from moles to moles. We can only ever switch substances that way. So I'll go from moles to moles of FCl3. Then I'm going to get those numbers from the balanced equation. That's their relationship. Those cancels. And now this time, because they want to know moles of iron chloride, they don't want to know grams, I get to stop here. I get to just stop here and do 0.35 times 2 divided by 3 into my calculator, which is 0.23 moles of iron chloride. Questions? All right. 15 tells us to balance the equation. All right. So, like I said, my kind of golden rule for balancing is to draw a line where the reaction arrow is, list the elements in the same order on each side, and do an initial count. So I have 3 carbons, 8 hydrogens, 2 oxygens. All right, so I got all of those from the subscript. So that 3, 8, 2. There's no coefficients out front yet, so I'm not multiplying those by anything. All right. On the right side, I have 1 carbon. I have 2 hydrogens. And I have oxygen in 2 different places. I have 1 oxygen coming from here and then 2 coming from here for a total of 3. All right. So now I need to make these tallies match on both sides in order to make them balanced. And what yeah, I need to add coefficients. That's big numbers out front to make them balanced. And so there's a lot of different, it's kind of just trial and error. The more problems you do, like the more patterns you see. So right now I'm seeing the fact that I have an odd number over here on the right. No matter what number I put in front of oops. Or yeah, I have an odd number. So I want to put some kind of even number in front of here to even this out because I'm only going to have even amounts of oxygen on this side, no matter what coefficient I put out there. So that's the first thing I see. That's like my first red flag. So I'm going to want to put an even number out front of H2O. Now I'm thinking to myself, well, what even number should I put outside of H2O? I can put 2, I could put 4, and I'm leaning, I could do 6, 8, whatever. I'm leaning towards 4 though, because if I did 4, 4 times 2 is 8, which is how many hydrogens we have on this side. So I'm going to do 4, so that way I bring the hydrogens to the same value. Now, that changed my hydrogens and it's also changed my oxygen. So I need to go back and do another count there. So now I have 4 oxygens here and then 2 from over here, giving me a total of 6. All right. So next, I usually leave oxygen for last, trying to make them even last. Once I get my words are escaping me here. Next, I want to tackle the carbon. I see I have 3 carbons on the left, and if I put a 3 out front of CO2 on the right, that will give me 3 carbons. It'll change my oxygen, but it's a risk I'm willing to take. All right. So now my hydrogens are the same on both sides, and my carbon is the same on both sides, which leaves me with this oxygen. I need to do a new count of my oxygens since I added this 3. So I have 4 coming from the hydrogen, and now I have 6 coming from this CO2 for a total of 10. 6 plus 4 equals 10. All right. Now, O2 over here is by itself, which is great because O is the only element I have left to balance. So because it's 10 on the right and it comes in pairs on the left, if I put a coefficient of 5 out front, 5 times 2 will equal 10, and it will be fully balanced. All right. So that's balancing. You only have one equation to balance on the whole exam. Any questions?
Can you
Yes, I
explain for the right side, the O, what is?
Say that again. Sorry, the oxygen. How I got the total of 10 or what?
Yes, how you get that up? Because I heard you say 3 plus 6. So it was
So
because
you multiply the big number that's out front. So here we have 4. It's going to multiply by the 2 here for the hydrogens. That's how I got 8 for hydrogen. But it also multiplies by whatever subscript is out here, which is an implied 1. So 4 times 1 is 4. So 4 of these oxygens came from that molecule, the H2O. The other 6 came from the CO2. So the 3 filtered out to the C, but it also filtered out to the O and multiplied by this 2. So 3 times 2 is 6. 4 plus 6 is 10. So there's 10 tallies.
thank you.
And I have a question on the right side for the carbon. So when you put the 3 in front of the carbon and it was already 1, and you added 2 more. I'm confused because I thought you would have added 3 more and that would have made it 4.
So it's that's why I use the tallies because it's 3 total. once I add the 3. So 3 times 1 for a total of 3. So that's why I only added then 2 tallies for a total of 3. I get what you see.
Okay.
I see the confusion for sure.
Okay.
But yeah, I just do the tallies because when you're balancing equations, you're always increasing the number, never decreasing it. So I find that easier than erasing. But if it confuses you, then go ahead and erase. Like write 1 and then erase to 3, something like that.
Okay.
All right. So question 16. All right. So now this brings us back to lecture 2. A nursing student has a sample of methane gas containing 3.1 times 10 to the 19th molecules. How many moles are found in this sample? So molecules, this is when we first started talking about Avogadro's number. All right. So we said, and that you would be given this on a reference sheet, that 1 mole equals 6.02 times 10 to the 23rd. And I like to substitute the word stuff because stuff could mean particles, it could mean molecules, it can mean what else have we seen? Compounds, atoms, right? This formula works for all of that. So this might seem like, I feel like the hardest thing for students is to identify when they look at a problem, what kind of problem you're dealing with. So my identifier here is, yeah, I see the word moles and we see the word moles in a lot of things, but I see the word molecules, which we only see in the Avogadro's number problem. So if I see the word molecules, I know that I need to go find Avogadro's number from the reference sheet. All right, so this would be given on your reference sheet. Then it's a matter of setting this up properly. All right, so our given value is 3.1 times 10 to the 19th molecules. So I need to make sure I put that on top. All right. Now I want molecules to cancel and I want to get to moles. And so that relationship is Avogadro's number, where 1 mole equals 6.02 times 10 to the 23rd molecules. So I'm out of molecules and into moles, which is what I wanted. Now, when you type this into your calculator, I'm running out of room. So I'm going to keep, even though this isn't going to be, this writing's not going to be for 17. All right, so in your calculator, you would want to do open parentheses, 3.1 times 10 to the 19th. And again, however you put that into your calculator, divided by open parentheses 6.02 times 10 to the 23rd. You want to make sure you're using parentheses to open and close both of these numbers, or else the exponents are going to get all wonky. PEMDAS is, well, without parentheses, PEMDAS is then PE, exponents first, which is not the order we're trying to go here. So you want to put those parentheses on there. All right, so when you put that into your calculator correctly, oh, I haven't pre-solved for this, dang it. So when you put that into your calculator correctly, you should get, and just give me a second, sorry, divided by 6.02 times 10 to the 23rd. Oh no. Okay, you should get 5.15 times 10 to the negative 5. And then this would be moles. All right, any questions? Okay. So 17. So let's read it and then decipher what the heck's going on. All right. So a student has 4 moles of C3H8. How many moles of hydrogen are there in the sample? All right. So right now I'm like, moles of one substance to moles of another? Sounds like stoichiometry. Yet I'm not given a balanced equation. Okay. So if you're going from moles of one substance to moles of another, but not given the balance equation, it's going to be this weird type of problem that we did like maybe 1 or 2 examples of, where basically you're using these coefficients to find the relationship. So you have 4 moles of CH3 on top, all right? So basically it's asking you how many moles of hydrogen, and it's referring to this hydrogen that's in the molecule, okay? So you're going to use this number as the relationship. So for every 1 mole of C3H8, there's going to be 8 moles of hydrogen. And again, I'm getting that from the coefficient number. Yeah, Tatiana, yeah, that's correct. I'm going to put a PDF of the periodic table, and then you can print it out and write on the back for your notes. And if you don't have access to a printer, I'm going to have a few copies at 5 p.m. next Tuesday if you need that hour to write on the back. All right, so we're out of moles of our entire compound. We're into moles of just the hydrogen. And so 4 times 8 is 32 moles of hydrogen, right? So this is the weird problem where it looks like it might be stoichiometry, but there's no balanced equation. And that's when we're going to use the numbers from the molecule or the compound itself. All right. Any questions? All right, 18.
Can you go back, or did you erase what you just wrote?
I erased it, but I can do this. What's up? What's your question?
No, I'm okay. I see now. Okay, thank you.
Okay. All right, so 18. All right, so 18 is a fun one because it is testing us on our ability to go from moles to grams, which is funny because that's a step you see in a lot of the other 2-steppers. So we've actually already seen this as part of step 2 of another problem. But, you know, whoever writes these tests, they crazy. Anyways, okay. So a student needs 0.45 moles of H2O. And now we want to know how many grams. All right. No stoichiometry needed. We want to know how many grams of specifically H2O. It doesn't list another substance. So if we want to go from from moles to grams, or even vice versa, we need the molar mass. All right. And so that's the number you calculate from the periodic table. But I will give you a bank of molar masses. So it is 18.02 grams per mole for H2O. So we're going to put our given on top, 0.45 moles of H2O. We want moles of H2O on bottom and grams of H2O on top. This number is married to the gram, so since we decided to put the gram on top due to wanting to cancel the moles, we're going to put that number with it, leaving us with 1 mole on bottom. Then we're going to multiply 0.45 times 18.02, and we get a number I have not solved for yet. 18.02 times 0.45, 8.0 no, sorry, 8.109 grams of H2O. Grams. No, that was the 9. That wasn't the G. Any questions? All right. Number 19. All right, so this takes us all the way back to lecture 1, talking about how many protons, electrons, and neutrons were in something. All right. And so to determine protons, electrons, and neutrons, we needed what was called the nuclear symbol, which is what we're given here. Now, this isn't stuff we can find on the periodic table. We have to be given it in this nuclear symbol form, and then we can decipher. All right. So with the nuclear symbol, we have the element. So in this case, it's Br. Here, we have the number of protons. So luckily, the number of protons is directly given to us. We have the mass number. All right, that's the top left. And then the top right is the charge. All right. And then we have different relationships here. So mass number equals protons plus neutrons, and charge equals protons minus electrons. So I'm trying to find protons, neutrons, and electrons. Protons are directly given to me in the nuclear symbol. So it's, for this case, it's 35. Neutrons aren't directly given it to me, but I'm given mass number, and I know that mass number connects the relationship between protons and neutrons. So I have 80 equals 35 plus neutrons. So if I did 80 minus 35, that would give me the number of neutrons. So 80 minus 35 is 45. So I have 45 neutrons. All right. And I'm not directly given the number of electrons, but I am given the number of, or I am given the charge, which shows me the relationship between protons and electrons. So my charge is -1, and that equals 35 minus whatever this number of electrons are. So if I wanted to get a negative number, I know that my electrons need to be bigger than my number of protons, and this -1 charge is telling me it's more negative by 1. So 36 is the number of electrons. 35 minus 36 would be -1. All right. Questions?
You explain that part one more time.
Yes. So charge shows us the relationship between protons and electrons, specifically that protons minus electrons equals charge. So if I have a charge of -1, which I do, that is going to equal 35, because that's my number of protons, minus my electrons. All right. So my charge is negative. So I need a number that is bigger than 35 in order to equal a negative number. All right. Since it's -1, I need to be bigger by 1. So 36 is bigger than 35 by 1.
Okay, thank you.
I'm sorry, Professor Daniels. Where did you get the neutron from?
The neutrons, so mass number, which is what's given us in the top left here, is protons plus neutrons. So since we're already given protons as 35, that's always going to be our bottom left number. Then I can find neutrons by subtracting my mass number from my number of protons.
Oh,
So
okay, I'll just write that here. Okay, thank you.
I have one more question. Will that 36 be a negative 36?
no, nope. All right. Any other questions? All right. So number 20, determine the molecular weight. That's another word for molar mass of barium chloride. So this is the example where they test you on your ability to calculate molar mass, that you know where it comes from. All right. So this is the one where I wouldn't actually give it to you on the formula sheet. You would have to know how to calculate it. All right. So if I have barium chloride, I have one barium and then two chlorine atoms. So I need to go figure out what the weight is of just barium and then what the weight is of chlorine. And so I got this 2 because there's a 2 here on the formula. All right. So this is where I would go to the periodic table. All right. So barium, Ba. Why am I? Oh, here it is. So 137.33. And then chlorine, 35.45. All right. So I would take this information. I might accidentally forget it. Okay. 137.55, 34.45. Let me go check that. 33 and then 35.45. Okay. All right. So then I add this all together. So I do 137.33 plus 2 times 35.45. And I would get the total value of barium chloride together, which is 208.23 grams per mole. Any questions? All right,
No,
21.
I'm sorry, can you go back right fast? One second. Oh, that's grams per mole. Okay, thank you.
All right, so 21. This brings us all the way back to lecture 1 when we were talking about temperature. And this is when I first introduced changing between different units. And so this would come from your formula sheet, but the relationship between Fahrenheit and Celsius is Fahrenheit equals 9/5 Celsius plus 32. And Kelvin, which we've already used this formula, equals 273 plus Celsius. All right, so that's what we need to solve this problem. This would be on the reference sheet. All right, so it says a temperature reading of 75.1 degrees is measured with Fahrenheit. So basically it's just telling us that this is Fahrenheit. What would be the reading in Kelvin? All right. So this is going to be a two-stepper because we don't know the relationship. Well, I'm sure there's a formula out there, but in our cases, we don't know the relationship between Fahrenheit and Kelvin. We know the relationship between Celsius and Kelvin, but not Fahrenheit and Kelvin. So we need to solve for Celsius first using this formula. And there's actually this would also be the inverted version of this would also be on your formula sheet. So let me write this down because it's going to be that, which we need the inverted version. Okay, so Celsius equals 9/5 times Fahrenheit minus 32. We want to make sure we minus 32 before we do, oh, it's not 9/5, it's 5/9 before we do the multiplying by the decimal. All right, so we want to do 75.1 minus 32. We can do that before we multiply it. So 75.1 minus 32, 43.1. And then we would times that by 5 divided by 9. All right, so then Celsius would equal 23.9. All right, so now we have Celsius. We can now plug that into this formula to get Kelvin, which is going to answer the question. So 273 plus Celsius, in our case, 273 plus 23.9 for a final answer of 296.9. So two-stepper, but you'll be given all the formulas. Any questions? All right, 22. All right, so this is written exactly like you would see it on the test. This also brings us back to lecture 1, talking about density, and specifically using density as a conversion factor. All right, so how do I know that though? So I see the word density in here, and I see it already given to us, meaning I'm not going to solve for it. I'm going to use it as a conversion factor. So this conversion factor, I know it's a conversion factor when it says a certain unit per unit, right? I don't want to start with a conversion factor. I want to start with my given. And in this case, it's 80.1 grams. All right. This problem, like I said, it's written exactly like it is on the test. And in this problem on the test, they give you temperature. You don't need temperature though. So when you see this density problem, when you see the word that has density, go to the temperature, crossed out. It's not a number you need. It's there to throw you off. So we're going to start with our given. Our given is, even though we're given density, it is not our given that we want to start with because you never want to start with a conversion factor. We're going to start with the 80.1 grams. And we want to go to milliliters. We want to go to volume in milliliters. All right. So now we're going to use this as our conversion factor. All right. So I'm going to put grams on bottom because I want my grams to cancel and I want mils on top. This number is always married to the gram. So it's going to go on bottom since I put grams on bottom, leaving 1 mil on top. Then it's a matter of dividing. So 80.1 divided by 1.23. So 65.12 mils. Question. Okay, so 23 sig figs. So this also brings us back to lecture 1, sig figs. So just a reminder, the rules of sig figs. So it's all about the zeros. Leading zeros never count. Never. Sandwich always. And then trailing, that's where it gets funky. So trailing has to be after 0 and non-zero digit. No, I'm sorry, after a decimal and a non-zero digit. Had a brain fart. All right, so this first one, 2.001, it's got sandwich zeros, meaning they do count, and so do all the non-zero digits. So we have 1, 2, 3, 4 significant digits. All right. Then we have two leading zeros here. Leading zeros never count. We have a non-zero digit, that's always going to count. We have a sandwich zero, always counts. And then we have another non-zero digit, which always counts. So we have 3 sig figs here. Next, non-zero digit always counts. Sandwich zero always counts. Non-zero digit always counts. Now we have a trailing zero. It is after a non-zero digit. It comes after that 1, but nowhere does it come after a 0. And so this is just a placeholder 0, and it does not count. So there's this 3 sig figs. Next, we have this number. I don't know if I ever showed us an example, I might have, with an exponent, but the exponent doesn't play into the significant figures at all. All right. So we only care about what happens before the 10 to the whatever. So we have non-zero digit counts, non-zero digit counts, sandwich zero counts, and non-zero digit counts. So this is also 4. Questions? All right. Chugging right along. Okay. So I gave us a lot of examples here, but there's only 4 questions in which you need to know how to name or identify covalent or ionic. But I just gave us lots of examples for extra practice. All right. So naming. This was in lecture 2. And there's 2 different naming conventions. It all depends on if you're covalent or ionic. All right. So that's the first step. I want us to go through and identify if these compounds are covalent or ionic. How do you know if something's covalent or ionic? So covalent compounds are between a metal and a nonmetal. No, I'm sorry. They're between 2 nonmetals. Between 2 nonmetals. And then ionic is between a metal and a nonmetal. All right, so, and if you're like, what's a metal and a nonmetal? Let's go back to the periodic table here. So here's the stair step. It's in the light green on this periodic table. So everything to the right of it is a nonmetal. So if we highlight up here, these are the nonmetals, right? So it's showing us in green and purple. And metals are everything to the left of the stair step, all right? If you're curious, this is ptable.com. I really like it. It's really cool. So like, I hover over this and it shows me all the metals. If I were to hover over just metalloids, it shows me those. Really cool thing. It's got so many other things going on too. But yeah. So let's go back to see what we're working with here. All right, so nitrogen and oxygen. All right, so we're gonna be flipping back and forth here. Nitrogen is over here, and so is oxygen. They are both nonmetals, so that's a covalent compound. So I'm gonna put C over here for covalent, because that's gonna dictate the naming rules that we use. But before we even get there, I just want to go through this whole list. Carbon and oxygen, we have it in two different forms here. So whether it's covalent or ionic, it's going to be the same. So we have oxygen here and carbon here. They're both nonmetals. All right, so this is covalent and this is covalent. They're just in different ratios. Hydrogen and oxygen. Oxygen we already know is a nonmetal. Hydrogen is over here, but hydrogen's like the exception to every rule ever. And so hydrogen is a nonmetal, even though it is way over here. It's the one nonmetal that's out of place. So this is also a covalent compound. MgCl. So magnesium is here. This is a metal. And then chlorine is over here. So it is a nonmetal. So this is an ionic compound. Chlorine, we already decided is a nonmetal, but let's go see where potassium is. Potassium's over here. So it's a metal. So a metal and a nonmetal. This one is also ionic. All right. So now that we've determined if it's covalent or ionic, let's do a little refresher of the naming rules. All right. So covalent is when you use those prefixes. All right. So you use prefixes based off of the numbers. So I will give those prefixes to you, but just for a reminder, mono 1, 2 di, 3 tri, that stuff. All right. And then there's the one little exception to the rule that if the first element is mono, then you drop it. All right. And we have two examples of that here. Refresher of the ionic rules. You just list them in order and then drop the ending of the second one, which you already do with covalent as well. All right. So covalent. I have a 2 after this nitrogen. So I'm going to call it dinitrogen. Then I have a 6 after this oxygen. 6 is hexa, so it's going to be hexa oxide. All right, you change the ending of the second element to "ide." You do that in covalent and ionic. Carbon, the first one is an implied 1, meaning it would be mono, but the exception to the rule is when it's the first element, you drop the mono. So this would just be carbon. And then my second element, oxygen, has an implied 1. This time I will say mono, so carbon monoxide or carbon monoxide. CO2, same thing, not monocarbon, just carbon. But this time oxygen has a subscript of 2 after it. So now it's going to be dioxide. All right. We have one more covalent compound here, H2O2. So 2 dihydrogen. Dioxide. All right. And then ionic is basically a simplified version of what we were just doing. So you don't have to list anything about the numbers. You just list the elements. So magnesium chloride. I totally ignore the 2. I just list chloride. KCl, potassium chloride. All right, any questions?
What does that say where you put ionic list in order dropping of what's that?
Drop ending, sorry.
Oh, ending. Okay.
Yeah, drop ending of second element. Which you do that with covalent as well.
So first we have to identify what they are as far as covalent or ionic and then name them.
Yes.
Okay.
All right, I'm gonna do 25 and then we'll end there. But I won't leave you hanging. I will create a recording for 26 through the rest. Um, I need to take a break for a second, like half an hour or so before I do that. Eat some food and stuff. But we'll do 25. Okay. So what would be the chemical formula of calcium and iodine? All right. So this calcium is, let's go back to the periodic table here. This is a metal where iodine is a non-metal. All right. So it's asking us to create a chemical formula for an ionic compound because it's a metal and a non-metal. So to do this, I need to know the simple ions of the elements. All right. So this is like when you get your periodic table that you're going to mark on for the exam. I want you to have this already on it. Let me read this chat. All right. So I'm going to erase what I have written. So pretend this is your periodic table. All right. So you're going to list the number of valence electrons. All right. So I'm going to do that in blue. And that's the trend where we just count 1, 2, skip a few, 3, 4, 5, 6, 7, 8. All right. That's valence electrons. I want you to also write the trend for simple ion, which I'm going to do in red here. All right. So that's +1, +2, +3, plus or -4, -3, -2, -1. All right. So you'll have this on your periodic table, right? Because you're going to write this on here. Then to solve for this problem, you need to know the simple ions of calcium and iodine. So calcium has a simple ion of +2. So here's calcium, and I'm pulling that from here, +2. And iodine here is going to be -1. Okay. So when I take this back to my sheet, yeah, okay, so +2 and -1. All right, so this is the thing where you swap the charges, okay? So calcium would take on the 1 as a subscript, right? But we don't write out ones, so I can just leave it blank. Iodine is going to take on the subscript of 2. All right, so this is where I swapped the charges. I should have maybe wrote this more like here. All right, so that's how I build the molecule. Any questions?
I guess I didn't get it.
So in order to build the molecule, we need to know the simple ions. Okay, so on your periodic table, which I'm going to post here soon. Why can't I find my mouse? What is going on? Okay, I see it on this screen, but not on. That's so bizarre. Okay, for some reason I've lost my mouse. Um, okay, so you go on your periodic table and you have the columns of +1, +2, skip a few, +3, ±4, -3, so on. All right. So for whatever formula you're building, you need to know those simple ions. So for calcium, I would go to the top of the column. I see it's a +2. For iodine, I go to the top of the column. I see it's a -1. All right. Then, to build the molecule, you swap the charges. So those simple ions that we pulled from the periodic table then become the subscript, the tiny number, for the other element. All right. So this +2 then goes to iodine as a subscript. Okay. Right here. This is where this 2 came from. And then the -1, we drop the pluses and the minuses, by the way, goes to the calcium. Only with ones, we don't explicitly write out the 1, so it's just calcium, Ca, iodine, 2, though, because we had a 2. Questions? All right, so we're going to end here. The next announcement I post will have a PDF of a periodic table that you can print out. We'll have a link for this lovely 2-hour session here of review. And then I will have a YouTube link for the rest of this review. So 26 through however many questions I have, 45. And then I should probably also make a PDF of just an answer key of this. So I'll do that and post that as well.
So I have a question. You had put in the I think it was the announcements. It was a periodic table and it was something else. Oh, and it was the midterm reference sheet. Is this going to be the same thing that you're going to give us on the day of the midterm?
No, so I didn't post those. Those are automatically in the Canvas shell. Like those are already
Okay.
Arizona College supplied, and you will have access to them on the day of the midterm, but they're going to be in your like exam. What I'm gonna post a PDF that you can print, and I'll also have printed copies if you don't have access to printer that you can write on, that you'll have access to. I will also print the reference sheets because a digital reference sheet sometimes isn't helpful. I also like to use it as scrap paper too for you guys. So I will print it as well. So yes.
So one more question. So will we be able to write our notes at home, like on the back of our paper, or that's something we have to do in the class that day?
No, you can do it at home. Like it's just you got to print the sheet yourself, and we're only in that predicament right now because of the snow day. Else I would have
Okay.
passed the periodic tables today.
Okay, sounds good. Okay. Thank you.
Yeah, thank you. All right.
Miss, will we have access to this recording?
Yes. Yep. So my next announcement, which give me like I want to take a shower and eat something before I make the next YouTube video here, but it will be the link to this recording and then 25 through 45. 26 through 45.
Thank you.
All right. So I'm gonna go ahead and end this. And then you'll see an announcement from me before probably 10 p.m. or so tonight.
Thank you, Professor Daniels.
Thank you.